This is Gen Java, easy Java for Erlang. I'm going to make sure I stand over here so I don't get blinded by that thing every time I take a step. All right, I'm Joe DeVivo. I work at Chef, and you can actually go to this site right now. This whole deck is going to be up there right now. There's going to be a lot of source code in here. If you want to read along there, there are also GitHub links so you can see things in their proper context if you choose, but pay attention to me. So yeah, I did this in org mode on Emacs, so if the slides get a lot crazy, just forgive me. Yeah, I want to get my cred there. So I write Erlang at Chef. I used to write a lot of Java, and those things are coming together right now. When I started at Chef, I worked on the analytics team. And our analytics platform is stream processing of all data that flows through Chef server, and it's used on clusters of up to, I think it's 40,000 nodes. I think I got this number wrong, and that's fine. It doesn't matter. It's big is the point. It sends alerts to various endpoints when various things happen on a Chef server. Various endpoints like HipChat and SMTP and webhooks, and more events coming soon, like really soon, like come to ChefConf next week and learn more. If you want to know more about this, buy my configuration management infrastructure. You can get it at chef.io. There's analytics documentation. All of these links are live links on the HTML version of this that I linked to earlier, so you'll get there eventually. So yes, come to ChefConf. It's next week. I'll be there. So our pipeline for the analytics server, we called it the Alaska pipeline. It's a storm pipeline, and Alaska has pipelines, and this is a pipeline, so we called it Alaska because we're very clever people. And what you do is you wind up writing rules for this pipeline, and here's an example of one. And it's, it's pretty straightforward. It just makes sure that you're compliant, you're PCI compliant, and you can't telnet into this machine in your infrastructure out there, which is good. You want to know that. And this is a complicated set of things that says that if we're listening on port 23, email security team at Financial Corp. So great. So we have to parse this thing in order to know what to do with it. And so we have this Alaska rules ANTLR grammar. It's based on this complex event processing language that you can find more about at these two locations, but we don't really need to go into that now because that's not what this talk is about. So what this talk is about is our configuration of this system, these rules, and how to set them. And we have this Erlang stack for that. And we use Erlang, Web Machine, and Squirrel to manage the configuration of the pipeline. And we want to validate these rules. And we had this ANTLR parser, but Dave loves writing parsers, and Dave's in charge of the project, so he gave us the Erlaska rules project. And the Erlaska rules project was like the Erlang version of Alaska rules. And it was a Neotoma parser, and the important thing you need to know about Neotoma and ANTLR is that they are different. So we had to write two grammars. And Alaska rules only ever validated that syntax. It never actually parsed them. Alaska rules is a compiler, and that code actually winds up running in the pipeline. So we're parsing these rules in two different ways. But the Alaska rules was easy at first, and we just had this little case statement inside our malform request callback in Web Machine, and that's great because it's easy. We just send this thing in. It tells us, is this thing working? Yes or no. Return a, I don't know, I want to say malformed request if it's wrong. Sean will correct me, though. So is there a problem here? Well, this worked fine at first, but every change to the grammar wound up being duplicated in two places. And every time we had to add features, it just kept creating more work for ourselves. And it didn't even matter because we never actually got to 100% compatibility between the languages. There were a couple of edge cases where one thing said it was valid and one thing said it wasn't. So what if we could just use the ANTLR grammar in Java? That would be, we already have the code. It's what's correct about the rule anyway. It's what we want to actually know. Is this thing going to be validated by our ANTLR grammar? If we did this, we'd cut our work in half, which was sad for Dave because that was one less parser he gets to write. So the easy thing would be just use this ANTLR, wrap it up in a static main function, and pipe it out to port command and call it a day. But I didn't want to. That was too much. I've seen those go bad before. So back when I was at Basho, I did the React JMX plugin, and that uses JInterface and does some stuff, and has a gen server, and it monitors and monitors the port that's running the JVM, and that I remember being a pretty sound solution, but it was way too specific to the problem at hand. So let's make it generic. And then I thought, well, if I'm making this generic anyway, I'd love to sort of obfuscate the Java part and just if you got to write some Java, you got to write some Java. But then you hide it inside the Erlang, and then basically we'll hide it with parse transform later, and you won't even know you're using Java, which is fantastic. And I decided to want to do that with an RPC call. Actually use the RPC module to talk to Java. So jinterface is a thing that we've had in Erlang forever. It's been here longer than I've been using Erlang, so as far as I'm concerned, it always has been there. And it understands the concept of nodes and EPMD and Erlang data types and process messages, which is great. It's a lot of building blocks that we can have to build an actual interop layer. And you can see more about JInterface here, the user guide. The Java doc's actually really important for writing your own GenJava functions, so good thing that link is here for your use later. But there's no RPC. But I do know a few things about RPC already coming into this problem, and that's that they're managed by this gen server. Well, I don't know it's a gen server yet. It's managed by this process called REX. It's a globally registered process, and it stands for Remote Executor, or Remote Execution Process, or whatever. So I go grepping through the code base of Erlang, and I find it deep in rpc.erl. Actually, the define is right at the top, but deep in do call, somewhere like many, many lines in. I can't see the link. 344 lines in, you'll actually see this do call function. And this thing is doing a gen server call to the REX process on node with this request object that's a mystery to me, and a timeout, which I know because it's gen server call. So let's keep digging. What's this request look like? Well, that do call function is called by call, and this is call, which all it does is wrap it up into a different kind of payload. So RPC call, we all know that. It's basic arguments are node and then MFA, right? Module, function, and arguments. So what we're doing is we're taking MFA and we're wrapping in this tuple, putting call on the front, putting group leader on the back so we can do some I/O. We're not actually going to do any I/O, so don't worry about that. And that's it. So it's wrapped in this 5 tuple now. So so if you want to dig into the source of do call, there's a link right here. There's some RPC magic in that we don't need to worry about. What we care about is that call is gen server call. There's some cool stuff with monitors and trapping exits and stuff. Go read the code. It's interesting. Not for us, not now. So this is what that request tuple looks like. We just pulled it out of RPC call, and it's this call atom, module function, arguments, and the group leader PID. But there's more. Why wouldn't there be more? So let's dig into gen server call. And gen server call will take this request object, and it will call gen call with it. And gen call is actually this for argument here. Look, I can highlight the line because org mode and Emacs and awesome. So we've got this gen call dollars atom because gen call is money. We got this we got this request thing here, and that request thing coming in from the call, which is that 5 tuple that we just talked about before. Is that it? Yeah. So we come over here, and then gen call, actually deep in gen call, you've got this Erlang send, and look at that. Look at that request. It's just a little part of it. But this whole line, which I'm going to highlight again because I can, this tuple is this label, this self mref, and then request. And this whole thing is the actual process message that's going over the pipe. So that's what's actually going out on an RPC call. This 3 tuple with a 5 tuple inside. And here I lined up the entire stack trace for you, and I tried to line up the arguments so you can see how this thing just sort of bloats as we go. So RPC call is just node MFA, and then RPC do call, it wraps it in that tuple, and then this thing makes sure that it's going over to Rex on the node you want, and then the money gen call, and then this self mref thing, and then this big Erlang thing is the thing that's actually getting sent over the wire. Which is great because now we know that. So yeah, gen call is the first bit that's getting sent over the wire. The second thing is a PID mref tuple. And the PID, that's just from, we all know from, we love from. mref is our return address. We're asking a bunch of questions over the wire. We're going to get a bunch of answers. What's the answer? What is this the answer to? mref's going to tell us. And then this request, which we've already seen and we're all friends with now. So great. Knowing is half the battle. We know what's coming over the wire. So let's set up Java to listen to it. Now Java gives us this jinterface thing, which gives us this node. So we create this node object, wrapped it up in a little main function that lets you specify the name of the node, and the cookie and stuff like that. And we create the mailbox rex, because we know rex is the thing that RPC call is looking for. And then this while loop just kicks around and receives messages and puts them out on the console. It's the simplest OTP node ever. So let's deserialize this message, this 3 tuple. this little itty bitty 3 tuple that we could pattern match and be done with in Java. Nope. This is just the part that makes sure it's a 3 tuple. And if it's not, we throw an exception, because it's Java. And then if that first element is gen call money, that's great. And if it's not, exception. Then the second element in that tuple, is it this 2 tuple? Is this 2 tuple a PID ref tuple? If not, exception. Now we check that last 5 tuple. This is the one we're really excited about. And if you notice, when we see that the arity is not 5 on this element, we're throwing an Erlang remote exception instead. Because the Erlang remote exception is this thing that we've created, which actually can send back error tuples to Erlang. We've gotten far enough deciphering this RPC call message. We've got the from PID, we've got the mref, so we know how to send a reply. Why not send a bad RPC message back instead? Explain what went wrong. And then we validate the MFA, and we do lots of casts, because why would this be easy? And I mean, this is a 65-line constructor, just where like a 1 case statement pattern match would have done. But it's the life I chose. So here's my error message. Here's my exception class. It actually has a to Erlang exception, which just creates error tuples so we can send back over the wire. And creating an Erlang tuple in Java is also annoying, because you have to create a list of objects, and then you have to actually populate that list, and then you have to create a new tuple and then stick the list in there. So, when you're used to Erlang, this is terrible, but Java guys are probably like, oh wow, 4 lines only? That's fantastic. So this exception, we actually constructed it with the mref and the PID in it. So it's got this send method, and all you need to do is pop a mailbox in there, and it's the Rex mailbox in this case, and it will actually send. We send it back to OTP. So we create this Erlang object, and this is creating what the response looks like. The response is back to Java is this other tuple, which is the ref that we talked about before. I'm sorry, the response back to Erlang is this ref that we talked about before, and then this reply, which in this case happens to be the error tuple, just error in the string that the error message is. So we wrap it up in this OTP Erlang object list, populate it, make the tuple, and what we wind up sending back is a tuple of mref, error, whatever, and we send it. And it goes, but sometimes not. This slide is mostly an artifact for the HTML people, but since you're here, we already talked about it. So then when we do this constructor for this incoming RPC call, what's happening is, that's it. We just catch the 2 different types of exception. If it's the Erlang remote exception, we send it back to Erlang. If it's not, we dump it out to the console. And on the Erlang side, we're monitoring the console through the port command, so we'll be able to put this in our logs anyway if this doesn't work out. So let's go back over there now and check that out. So the Gen Java module is a Gen server. It kicks off this a jar of your choosing in the with the port command. And when you build that jar, you include the Gen Java jar file. So what's the Gen Java jar file? Well, let's talk about the Gen Java project for a second. This is on my GitHub. There's links in the talk, obviously. It's got 2 source trees, source main Java and source main Erlang. And one builds a jar that goes up to Maven Central, and one bit's rebar dependencies, so you can pull them both into whatever projects you use. Let's see here, yeah, so we do that. So you start the Gen Java server, you open a port running on your jar, and you've made this jar, and you've included my Gen Java jar in your jar, and you're using, well, we'll get to what you're using later. So what we've got here is a basic startup for this. This is in my init of my Gen Java Gen server. And what it does is it essentially just keeps asking this Java node, what's your name, what's your name, what's your name, what's your name, what's your name? And it's going to keep saying bad RPC, bad RPC, bad RPC, until one day it doesn't. And when it doesn't, it's going to say, well, here's my name. And I know what your name is because I just named you like 3 lines up in the init call. So, because that was the command line argument to my main method, right? So then when that happens, we actually can we can link to this process. We can set up a monitor. We can set up a callback. And we've been fetching name all the time, but we finally have made fetch happen. So that's actually animated. It'll be animated on the HTML deck. I couldn't animate GIFs in Emacs. There's only so much a single man can do. So this handshake, yeah, this explains what the handshake did. We do the RPC call for node. We do a link. We do a monitor. We do this init callback. This init callback is something that sets up state on the JVM side. So if we want to make RPC calls over to Java, and that Java process happened to need some initialization, maybe read in a file or something, hypothetically, then this init callback will actually do that. And then this error log. This is the handle info of my gen server, and all it does is it looks for the port that's running the JVM, and it matches this data tuple, and then it spits it out to logger. So anything that comes out on the Java system console, it's coming out in your logger logs, so you don't have to look in like many places for this stuff. It's all there. So yeah, so now we're sending RPC calls to the Java node. We can send error messages back, and they can come over as either console messages or RPC responses. So what about actual RPC calls? I mean, this would be pretty stupid if all I could do was send error messages back. Well, the easy way is to hard code some. And I hard coded these 6 because Erlang node and Erlang link, you've already seen me do RPC calls to these in my handshake, so I have to have them. And Erlang absolute value is just sort of my proof of concept method that I could do Java absolute value and send the answer back. And then I did some Java inspection stuff, which was really cool. So like Java system properties can just come back as a prop list for you if you're interested in dumping that out in the beginning of your logs or whatever. So what is this Java module? I made it up. I have a Java class, java.java. It's fantastic. But let's, I think we get to that maybe 2 more slides in. So let's talk about Java functions that you're making yourself. I kind of use methods and functions. They're methods in Java, but by the time we get through with them, they're going to be functions because they all have to be public static final. And they also have the arguments and return types specified by JInterface. These are defining your Haskell, sorry, fast forward, right? These are defining all of your Java, your Erlang types in Java, and Erlang knows how to, JInterface knows how to send them back over the wire. And since Java reflection is a bit expensive, we're going to actually cache these method objects as we find them. So how do we do that? Well, we create this method cache, and it's got this Erlang function cache key thing, and that's essentially our MFA from before, right? It's our module function and our type signature of the input arguments for the function. The return type is actually not involved here. And it's that Java varargs thing, so this absolute value thing takes 1 argument. It's an OTP Erlang double. I had to actually create 2 signatures for this, 1 for long and 1 for double, because it can send both across the wire, and I want to answer the same question with both data types. So basically now, if I ask for RPC Erlang abs and I pass it a double, it's going to find this method from Erlang class, and it's going to run it for me. And if I pass it along, it'll run that one, which is bad because I can make them behave differently, and that would be, but I have to be a good Java programmer too, don't I? So here's my java.java module. No, it's not. It's the RPC cache for it. And it's just these simple things that I'm doing. I've created these 3 functions that they're all wrappers for Erlang data types for Java functions. And here's java.java. Here's system properties as an example. And you see this annoying stuff I have to do to doing all this typecast. But the meat of this thing is right here, system.getProperties. And the rest I just iterate through and I'm basically creating a prop list, which eventually gets returned here. And that looks like this. I connect to my Java node and I run system properties, and sometimes they look like little single quoted atoms and sometimes they don't, because that's how we render things. But yeah, that's Java system properties. So what about your own methods? Your module is going to be your full Java class name, package and all. The function is going to be the method name, and the args are just going to be the list of argument types, and you should know what they are because you wrote the function. And then we just go into the cache and looking for them. When a message comes in via RPC, and we've already processed it using all our casting and Erlang tuples and stuff like that, then we pull it out of the cache, and then we tell the message, oh, you want to execute this method, and then we throw it over to the pool. Otherwise, it's not in the cache. So we try and find it. If we find it, put it in the cache. Set the method on the object and put that in the pool. Otherwise, it didn't work, and send bad RPC. What do you mean send bad RPC? Well, I got to scroll down a little bit. Look at that. Look at that. 2 bad RPC. We've all seen that, right? I built it with Java so I can answer bad RPC calls when you have an undefined function. I actually send it back and say, that's not a defined function. This link is to that Java function, and it's really long. Because you remember how annoying it was to build one tuple? It took like 4 lines of Java. Look how nested this tuple is. It was a nightmare. But, you know, it's always the same, so why not? I just did it one day. And so the payoff here is that reflection is only once per method. Now we talked about the pool, right? That's what we're aiming for. What we want to do is we want to just do multi-threading on this thing in case, you know, we ask it hard questions. We don't want to bottleneck the whole thing and just have one big line of processes waiting for messages to come back. So we just did some Java connection pooling, and each message has this run method that just kind of, you know, does a method run invoke, and if it works, then that's great. This is our result. Otherwise, we catch an exception, and we do this error wrapper thing, which I thought was going to be on the slide, but it's not. But guess what it does? Error tuple, error and string, send it back. This sends the result. You know, the result might be the exception output, it might be the method invocation, it might be the OTP Erlang Atom null. Probably won't be. And then that's it. But now we've got to wrap up this response because, you know, we can send things back to the front PID, and then we're wrapping this response. But wrapping the response, well, this looks familiar, doesn't it? I clearly repeated my code here, and I'm going to have to go back and refactor this. But I didn't want to do it before the talk because I already had all my links with all my line numbers hard-coded. So I'll do it later. And this send, make sure to send it to the right place. Wrap response is grabbing our from ref from before so we know where it's going back to, and then send it back. So what's the Erlang developer experience actually look like? Well, you might remember I'm a little crazy about user experience, and if not, go check out my Cuttlefish stuff. This is all your Java module really has to look like. Your module is whatever you want to call it, and throw this parse transform on top. Then you configure this thing. GenJava can have multiple modules in your project, so you have a list of modules. This one is my Java. This is where you find the jar, and that's how many threads you want. That's it. The Erlang server node thing is all part of the GenJava jar, so it all knows what package to use and everything like that. You want to start it up. You can start it up with start link, or this nice little child spec. Where'd start link come from? It's all in the parse transform, guys. So here's an example of one of the things we do. It's a wrapper for 5 GenJava functions. The first one is call. Actually, I thought I'd do a more complicated example, so I did call here. But what you can do here is just say my Java call, then give it your package name, your function name, and your list of arguments, and you'll get a response. And your response can be anything your heart desires, I guess. So you have 5 functions for free here. What do you get? You get start link, start, call, and stop. And all they do is take these gen server functions that we already know and love, and we just sub our module name into all of them. Because I didn't want you to have to type your module name all the time. But that's it. That's all it does. I thought it would be very convenient for everyone. See, there we go. And then, so you can throw your init callback in here. This is the thing that actually runs that state initialization stuff, and I'll show you a real-world example of that in a minute. And then you could write convenience wrappers, which I really like, and I do this all the time. First of all, I gave you that dialyzer type for bad RPC, so you can do your own. You can say this is what I want to return, but I can also return a bunch of stuff that GenJava will try and return. And then you can just create your method, create your arguments, and then wrap it in this call to your module and function and everything. And then this is what your use case looks like. This is what the program actually does when they're trying to call Java. So that's pretty easy, I think. I hope. So let's bring it back to my analytics problem at hand. Alaska rules, the Neotoma parser is out, and Alaska rules.jar is in. We set up our sysconfig to have some parallel threads and to point at our Alaska rules jar, which includes the GenJava jar. And here's our module. It just declares the module. It's got the parse transform, a couple of functions. So we've got the valid rule function, which has a couple of types it can return, including bad RPC. And it calls our Shep Analytics Rules Erlang Rule Validator, which is a wrapper with OTP types for our actual rule validator function. We have another concept called rule groups, which is more than one group. It parses a little differently, but it's the same general idea. And then we have our, here are those functions on the Java side, right? They're very simple. This class has some state, which includes the compiler that's been initialized once and just lives in memory. And then we'll take the binary in, we'll turn it into a string, We'll parse it through the Antler parser, and then we'll send back an answer. And the answer can either be, yeah, that's great, or nope, here's an error string. It actually gives you like a meaningful, your rule did not parse at line 12, character 17. So that's great. Now, if you noticed our rule before, it had some it described some events in Chef and some attributes of those events. And those relationships we actually have described in some JSON schemas. So our init callback will actually send over the JSON schemas over to the Java node, and it will load them into the rule compiler before we actually accept any RPC calls. All right, so bringing it back to Web Machine, now I can use my Alaska rules gen Java module, call this valid rule group function, get the rule out of the Web Machine request state, and then see if it's good. If it's good, great. This request is not malformed. If it's an error, we're going to send back an error message that's actually going to be some sort of essentially error tuple in JSON that goes back to the UI, and the UI says, nice, cute little red text at the top. Oh my God, your rule is a little bad, but you can just tweak it, and we love you so much. So just do this one thing for us. And then if Java's broken, then it's a server-side error, and we're just going to stop deactivate. All right, so wrapping it all up, this is just a wrapper. Erlang did the really hard stuff for me. It gave me all these nodes and classes and stuff. I just wrapped it in a gen server that monitors it and integrates it really well and put a parse transform around it so we forget it's Java. But that made the project easy. Didn't have to make it easy. I wanted to kind of prove that I could do this, that this wasn't limited to like a Java thing. And I'd been meaning to learn some Haskell. And it always seemed really, really hard. So I figured if I can make this work in Haskell, then I can make it work in any language. So I'm going to give you the source here to my attempt at that. This is the Erlang Haskell interface 0.2. Why 0.2? Because 0.1 existed. Erlang gave me no Haskell, but somebody did. I mean, it was somebody 8 years ago, and it doesn't work anymore, but there was something there. So I went and looked at it, and here's what I actually got out of it. Somebody made me a data types for Erlang, so I used them. There were these packaging functions for like putting bytes and stuff on the wire, so I used those too. And they gave me half a protocol. It looks like what they were trying to do was implement a way for Haskell to send requests over to Erlang. And I wanted to do the opposite, so it looked like they didn't bother doing that other side of the protocol. So that was my goal. It used this nano MD5 dependency, which no longer works. So I had to replace that with pure MD5, which wasn't that bad. And the existing documentation isn't great. It could have been me that was the problem. That could have been operator error there. So I tried to spin up an Erlang node in Haskell, and this is what I did. And I'm going to walk you through that right now. I've got this create self thing, which does that same thing that we were doing essentially with our main function before. We're creating this node, and we're just going to sort of listen there. And then we've got this mailbox that we're listening for messages on. We're going to start routing those messages. There's a lot of forking. You're going to see a lot of fork IO here. And then I've got my little Rex mailbox down here. They're actually listening for Rex requests. In theory. Let's see if it actually does anything. Well, this create self thing, it's going to run these two functions basically, this serve and self. And then if you notice down there, there's also a little create mailbox for netkernel. Because if netkernel's not running, then you can't ping the box. If you can't ping the box, then you can't do anything. So there's this serve function, and that thing connects to EPMD and opens up a listener and then puts messages in an mbox. Let's talk about EPMD. Here's some great links that you can read, and when you read them and realize that I took a week off at Christmas time from my family to read these documentation, you're gonna feel a little bad for me. But what EPMD does is it reserves, EPMD sits there and it reserves ports and tells you what Erlang nodes are listening where. And what it does is it sends this message over, which is basically the same always, except for the port. I can do this. Which port it's reserving. This is usually the same. It's just an Erlang node, TCP/IP. This hasn't changed since R6, I guess, which is do with that what you will. This is how long the node name is. This is the node name, and that other stuff we didn't even use. Think of like chess. Remember when you were like a kid and you played chess and you moved the piece, but you weren't sure you're going to move the piece, so you just left your finger on it? That's EPMD. You move the piece and you're like, yeah, I'm going to be port 6.5. Well, I guess you can't be 6.5, but I'm going to be 6.4, 3.2.1. And you just hold it there. And this socket stays open forever. Just letting you know, on that port. It's not open on that port. It's just talking about that port. If you close that port, if you close that socket, the port is no longer reserved. So what's that look like? Well, Wireshark apparently understands EPMD, which is fantastic. Look at that. We've sent our little signal, and we get to the live to request, and there's the port number, and there's where it's going to. Fantastic. Look at my little Haskell node name there. Look at it in the bytes there. It's fantastic. It answers. Look, it's got a live to response. There's my answer. It's a lot more gibberishy, but I'll take it. It's an answer. Meant that it understood the question, right? So here's how we do it in Haskell, right? We've got this little put monad thing that you just throw these little attributes onto it. This is the port number. This is the tag of the message. This is the version, stuff like that. And it goes. And then you keep the socket open forever. This is really difficult to get that working, actually, but it works now. So yeah, so that's just EPMD. Now the two Erlang nodes have to talk to each other. And they've got this little song and dance that they do here where what's your name? Oh, well, that's a great name. This is my name. Oh, well, that's great. Are you ready for a challenge? Yes, I am ready for a challenge. Oh, what's your cookie? Oh, well, we don't really know each other that well. So, eventually we tiptoe around it, and 18 months later, we're married, and this is an example of one of the packets that comes over that. So this is a short way of saying that it opens, so that serve function, right? It opens up a socket on port X. Then once that port is open, it knows what X is, so it tells EPMD, yeah, sure, I'm open on this port. And then it does the distributed Erlang, Buffalo two-step. And then it eventually winds up just receiving messages on that socket that's open for dispatch. What's that? Well, we'll get to that first, but I'll show you the Haskell that does that. So this is the serve, and it opens the socket, and then it sends the alive to request, which of course has to be a fork because it has to stay open forever and can't do anything else. And then we have to create this mvar, which is just a place where we store state for this connection, and then we process requests. Well, what's process requests? It's this. Let's see here. We just read stuff in off the socket. Every time we smell something coming in, we just send it off to process messages, which is cool, because process messages just sets up a send and receive buffer and just starts pulling information and sending it back, and that's it. And this Erl connect thing here, this is the handshake, back and forth thing that eventually winds up giving us a to and from, pipes to send information over the socket. And then now that we are connected, we actually tell the state of the whole self node that we are connected. So great, so node receive, what does this thing do? Well, it just sort of sits there and listens for stuff, and sometimes it's just a heartbeat and it does nothing, and other times it puts this Erl dispatch tuple thing on the outbox. What's this Erl dispatch tuple thing? Well, it's this. This is the distributed Erlang middle syntax here, and there's maybe 13 different things you can send. We're only interested really in number 2 and number 6, which are registered send and actual send. Send is just to a PID, registered send is to a named PID, and named PID like Rex. So maybe 6 is the one we really care about. So we have this self thing, which is dispatching all these things. So the dispatch call comes in here, and we match the pattern here, and then we say, well, is this thing a number 2? I left out a bunch of this because it's like a really long case statement. But is it a number 2? Yes. Then we look over our PID mailbox and we send a message over. Is it number 6? All right, we'll send it over to that PID instead. But these PIDs are all little mvars that are taking information off some Haskell thing I didn't quite understand, but it worked, so I just backed away. So there we go. And then here's the net connected node that just manages the state of what nodes are connected. So that net kernel mailbox we opened up, this one was really easy. We just sit here, and anytime anything comes in, we go, yep. Which is the answer I want from ping, and I never got another question from net kernel, so this made it work again. So what's an RPC call received by Haskell look like? Well, if I'm on the Erlang side and I send an RPC call to this Haskell node, would you look at that? Gen call money, Erl tuple, PID ref, Erl tuple, call, module, function, args, Erl PID, that's group leader. This, we're in familiar territory. I'm actually getting a message that I understand from my Java days, which seems so far away. And while they were manual labor, but it was easy to understand. So yes, and now I have this Rex mailbox handler, and this thing I can just do this pattern match that puts together this tuple and understands the PIDs and the refs and everything. And I can start hard coding functions that I need from my handshake, right? Like remember Erlang node nothing? Well, here it is, and it just Haskell doesn't like when I, something about the IP address, so we have to manually add it over here. It's fine. This is very brittle, but you know what? It works. Every answer to every other RPC call here is going to be just Haskell equals var yes. Wow, I'm almost done. So yeah, notice I'm just returning Haskell equals var yes for everything. I'm just excited it's working. There's plenty more to do. Is there anything more on this slide though? No. Like Gen Haskell. Oh my God, I did this yesterday because I got the idea and I thought maybe I could pull it off before the thing, and I did. So here's a GitHub link, var yes, to Gen Haskell, which is pretty much a copy paste of Gen Java, only where the port command starts, it spins up this Haskell process instead of the Java process. So, I mean, the idea is we could even make gen, underscore asterisk language and just set up the callback for the port command, but that's, that's even further in the future work. So yeah, and it works. Look, I created this RPC test app, which you can also see, and it has two dependencies, Gen Java and Gen Haskell. And I can start it up here, and it starts up Java. Look at those output getting caught by the, by the output of my Java and my Haskell. Here we go. And then we get down to our console, and I could say my Java, call Erlang node, and it goes, great. There it is. It's got this convoluted name because I do it as an underscore, I do it as a combination of the Gen Java and the module name that we created and the app that we created so that it would be unique. And look, and I can do it for Haskell too, and it creates the Gen Haskell, my Haskell RPC test node. And they answered that question correctly. So I tried, sending Haskell my call about Erlang node 1, and Erlang node is undefined. So it's just going to say Haskell equals var yes, because it says that to everything. And then the Java one just said we do try Erlang node 1, and Erlang node 1 comes over, and it goes, yeah, I don't know what to do with that, but I'm Java, so here's a class cast exception. And then I get out of here, and look, it tries to send Rex a stop message to shut down. Java goes, great, I'm going to shut down. And Haskell goes, you didn't implement that yet, so this GHC process goes rogue and kills my computer. So this is also supposed to be an animated GIF, and you can see that on the thing. But since we are done now, I'm going to quit out, and I'm going to open it so that you can actually see my demo. And then we'll be done. And then we can answer questions and stuff. So we're going to do open index.html. There it is. That looks terrible because I'm not connected to the internet. But the important thing is this animated GIF, which I'm going to open in a new tab so you can see it. There it is. And look, I'm opening up EPMD in debug mode. And we are starting up an Erlang node. And you see EPMD debug mode is saying all this cool stuff about what messages it got. And then you see over here in the Haskell thing, I'm going to start this Haskell process down here, and it's going to register with EPMD. Look at that! Whoa! There's my Haskell node. It's this demo, this contrived demo is fantastic. I can just narrate it. And then over here, I'm going to start asking questions about something. Maybe I'm going to try and ping the Haskell node. Look, I did, and there's some output about what message it pattern matched. And this code's all on GitHub for you to play with. There's tons of links in this thing. So you can go to joedevivo.com/ef2015 and check out all my source and my slides and stuff like that, and throw tomatoes on me on Twitter or something, or we can talk more languages if you want. Thanks. Yeah.
Do people at your work know what you do during the day?
Yes, they do. Like I said, Dave loves parsers, and he was sad to see his go. But he was glad that he didn't have to maintain the two grammars at the end of the day because he has lots of other work to do. Eventually, once I made this Java thing and got taken care of that, I realized I was working too much Java, so I switched teams, and now I write Erlang on Chef Server all day. Anybody else? Yeah. You. Yes. We talked earlier. What?
I know a guy I used to work with works on GHC, the Haskell compiler, and there's actually a way to define DSLs for Haskell called quasi-quoter. So you can actually make the Haskell version of Erlang look more like Erlang and maybe even do normal tuple notation, but have to do all the typing if you want to.
Oh, fantastic. Yeah, so I wrote Haskell for 1 week ever. This was my not only excuse to learn Haskell, but to prove that if I could do it in Haskell, I could probably do it in other things too. But yeah, that's fantastic. John Hughes.
Yeah, so something else we're looking at in Haskell is Cloud Haskell, which is supposed to provide Erlang-style distribution for Haskell.
Yeah.
So wouldn't it be cool if it could look like Cloud Haskell from the Haskell side, and like Erlang distribution
Yes, everybody, John, you just told me that it would be awesome if I could make one side look like Cloud Haskell and one side look like Erlang RPC calls, and absolutely, that'd be fantastic. So I saw Cloud Haskell about 2 years ago, and I know it wasn't ready for prime time then, but I wasn't even ready for like ground Haskell then. So now that I'm sort of tiptoeing into Haskell, I'll get Reed Draper to show me Cloud Haskell and make me feel like he knows everything again. All right, are we good on time? Yeah, it seems about right. All right, got anything else? Anyone?
How long did it take?
So it is a lot. Do you mean the Java stuff, the Haskell stuff, the everything?
Java stuff separately and Haskell.
Okay, so the Java stuff I got to do as part of my day job, but also sort of like interspersed through other things. So it's harder for me to quantify like how much time that took, especially because we tiptoed around it. It took us a while to sort of discover that we didn't want to use the Neatoma parser, and then we did a really bare bones version of this that wasn't generic at all, that just spun up a Java server inside the Alaska rules jar and did all this stuff very hard coded. And then, once that was done, we generified it. And generifying that, I would say, took under a week, but it was getting to that point that was probably, took maybe a month or so, off and on. The Haskell stuff, on the other hand, was very time boxed. I had a week. And if I couldn't, I had 2 weeks off for winter break. The first week had Christmas in it, and the second week my wife said, I'll watch the kids. You just, if you can get this done by Erlang Factory, it'll be amazing. So, mad props to my wife for that. Who's right there. And yeah, so it took a week. I had this thing sort of ping-ponging back and forth Friday around noon, and I was pretty excited about it. And then some of these the Gen Haskell stuff, the app that we did that last sort of console trace from, that thing took, it didn't exist before I got here. So a couple hours. Anything else? Yeah.
The Gen Java stuff is, you have an argument in there for 10 threads. I assume it is one JVM.
Yes.
Have you tried it? How's the performance?
So far, it's gotten everything we need. Like, we're running analytics on, systems with 40,000 nodes, and now granted, it's not a high traffic part of the analytics pipeline, right? This thing's getting events all the time, and it's routing them and everything, but those rules are already compiled and in Storm. This thing just validates rules when somebody in the UI changes the text and hits submit to web machine. So I don't know if we've really pushed this as hard as we could. Casey.
So I assume the next step is to push out Storm, because that's clunky and janky and use Erlang for the network.
Oh, sure. We talked about, what was it, Esper, I think? I don't know, those decisions are above my pay grade. I just wanted to write Erlang. They said they want to do it in Storm, so Dave went and did the Storm, and I did this. All right. Was that next language? I don't know. So the biggest problem with the Haskell thing right now is if I leave it running for too long, it starts pegging the CPU. So maybe fix that before I. It works. It doesn't work well. Yeah, sure. No, we've got to give Web Machine some love next. That'll probably be the next project. All right, guys, stick a fork in me. I'm done.